Today's lesson is on compound probability. Compound probability means that we have multiple events. Those events can be independent or dependent. If the events are said to be independent, that means that it's with replacement. Like say you're drawing marbles out of a bag. So if it's independent, you would put the marble back in after you draw it the first time. If it's dependent, you would keep it out. But the main thing that I want you to understand is that if it's independent, the probability does not change due to prior events. Okay, if it's dependent, that means prior events would affect your probability. So your probability depends on what's already transpired. With compound probability, it is very important that we always assume success with prior events. We're going to do the probability dealing with a standard deck of playing cards. So I first want to make sure that you know what's in a deck of cards. There are 52 cards. Okay, there's 13 cards in each suit and 4 suits. So 4 times 13 is 52. Or you could just say that 1/4 of the deck is clubs, and this is the symbol for clubs, spades, hearts, and diamonds. So we have 4 aces in the deck, 4 twos, 4 threes, so forth and so on. Jacks, queens, and kings are said to be face cards, okay? So in the deck, we have 3 times 4, we have 12 face cards. Aces are not face cards, only the ones that have faces on them. So if you ever have a probability question that asks about face cards, I want you to know that. When you find the probability of multiple events, you multiply those two numbers together, those two probabilities, which are likely to be fractions. Okay, example 1. Find the probability of pulling a club, then pulling a red card. And that's without replacement. So we have this deck of 52 cards, and we want to know the probability that our first random draw is going to be a club. I'm just going to say that's our first event, or event A. And then the second draw is going to be a red card, and I'm going to say that's event B, or just the second event. So the probability of A and B, so we want to be successful at both of those, is the probability of A times the probability of B. So the probability of A pulling a club, 13 out of the 52 cards are clubs. Or we could say 1/4 if we reduce our clubs, and the probability of pulling a red card. Now it says without replacement. So now B is affected by what happened with A. So we no longer have 52 cards in the deck because we took one out. So there's 51 cards left in the deck. Now, did us pulling a club out of the deck affect the number of red cards? Not at all. So there are still 13 diamonds and 13 hearts. So notice here, we say that the clubs and spades are black cards and the hearts and diamonds are red cards. So there are 26 red cards left in the deck, even after our first draw. Now again, notice that I took that down because I took one club out. So that's why we only have 51 cards left. Now, if we multiply this together, and I just reduced the first fraction to make it easier, we have 26 over 204, which reduces to 13 over 102. You can present your probability as a reduced fraction, or you can punch it in your calculator and list it. We call this a frequency or a percentage by moving that decimal twice. You can present this any of these three ways would be just fine. Now, we know the closer to zero we are, the closer we are to 0%, this is pretty unlikely to occur. That if you pulled two cards, one and then the other, that the first one would be a club and the second one would be a red card. Pretty unlikely. Alrighty, moving on. Example 2. A bag contains 20 $1 bills and 2 $100 bills for a total of 22 bills in this bag. If you are allowed 2 pulls, what is the probability of getting $200? So you're going to pull the only 2 $100 bills out. So the probability of getting $200 on those 2 pulls, the first pull, now mind you, when you pull the bill out, you're keeping it, okay? You're keeping it. So there's 2 chances out of 22 total bills. Now, remember, you always assume success. So we're assuming success. So now there's only one $100 bill left, and there's only 21 bills in the bag. You see how that second probability is affected? So now on top, 2 times 1 is 2. Actually, let me reduce this first. That just makes my arithmetic a lot easier. So now I have 1 over 11 times 21 gives me 231. And that's a good way to present that probability. 1 in 231. And if you were to write that or find the decimal, you would say, wow, that's pretty unlikely, okay? Furthermore, you could write it as a as a percentage by moving that decimal twice. So that is less than 1%, okay? So again, pretty unlikely. Sometimes you'll even see these written as like 4 in 1,000, 4 in 1,000, like say this were a game, and you could say 4 in 1,000 would win this game. Okay, that's just another way to look at this if you move into statistics. Now, I like to make sure you know these 2 ways to visualize data. The important thing about data is organizing it so that we can easily digest the data. So let's say that I surveyed a class and I asked how many students were musicians that wore glasses, okay, or contact lenses, and let's say 8 people. And then what about musicians that don't wear glasses, and let's say it was only 2 people? And then what about non-musicians that wore glasses? And what about non-musicians that don't wear glasses? Had that many people. And Assuming that everyone participated and answered, how many people were there surveyed? Well, you could add all these numbers up. 8 plus 2 is 10, 7 and 13 is 20, so that's a total of 30. And you can always add across, and your numbers should check out, or you could add down and across, and your numbers would check out. But there's 30 people total. That's a tongue twister. Oh my gosh. 30 people total. Okay. Another way that you could illustrate this same information is a Venn diagram. So how many people, if I were to make my bubbles musicians and people that wear glasses. So there are 8 people that fall into both categories. There are 2 people that are musicians but don't wear glasses. And there are 7 people that wear glasses but are not musicians. Now, you want to be careful that you don't count anyone twice, okay? So total, this is 17 people, and we also know that there are 13 people that are non-musicians, no glasses, okay? So you would just put them in the group, but outside of those specific bubbles. Now, you'll develop a preference as to which illustration you prefer. I personally like two-way tables, but some people prefer Venn diagrams. Let's answer a couple of questions and use these visual organizers. What is the probability that I randomly select a musician with glasses? So if I just pick one person at random, and when we say random, that means without bias, being fair, everyone has an equal chance of being selected. Then how many people were in there total? 30 people. How many people are musicians with glasses? Musicians with glasses, 8 out of 30. So I could reduce that, present the answer that way, or as a percentage. I like percents because I know 0% is impossible, 100% is very possible. This is possible, but not very likely. Okay, so you could present this either way, and I always ask myself about the likelihood of something occurring. Let's look at this last example. Given, that's a buzzword, okay? Given that I select a non-musician, that's a condition, okay? That's a condition right there. And we call this conditional probability. So given that I pick a non-musician, what is the probability that they will wear glasses? So what this means is that my total only considers non-musicians. So when I go up here, I'm only looking at these 20 people, okay? So my total is 20. Now, how many of those 20 wear glasses? So out of the non-musicians, how many wear glasses? 7. So 7 out of the 20. That's what we call conditional probability. Or if you punch that in the calculator, 35%.